Okay, we're started. I believe the 25th, is that correct, of September 2012, a Tuesday, a lab day. The help session for Lab 2 is where we're at in the course. That's pretty much on your own, as you've already figured out, whether you're local or distant at this point. I've posted all the files, the compiled data set, and a template for doing some bioenergetics analysis. That's been up on the web since Sunday evening. I think at the point when we posted that data, we had 15 data sets from the 29 of you who are registered in the course, so we're a little short. But the instructions are that if you are among the 15 who submitted data and your initials appear, then you are to delete your observations, your personal observations, so you'll be working with 28 replicate observations on each of the 4 treatments. If, on the other hand, you were among those who haven't submitted anything or hadn't submitted anything by the time Donovan compiled the data and sent it to me, then I'd like you to add your observations to the data set. So you'll be working with 32 reps instead of 28. So that's plenty in either case. And people who haven't submitted anything by the way of personal data still need to get those in, because I think there's going to be a late charge if you don't submit the raw data to Donovan, just to let him know that you did it. So that's number 1 on the agenda. Number 2 is to try to update you about a couple of things. One is the Stella order that I just made yesterday. So those of you who are graduate students in the course and my one honor student who's an undergraduate who's going to be doing a project are going to be notified by Anna, the daughter of the guy who founded Stella, or who developed Stella. She's a marketing person with the company now, and she's going to be notifying you about your registration and download of Stella 9. You don't need Stella 9 to, as you've already discovered, to play back everything in the course, but you do need it to provide you a way of saving models, which you will need to do if you're Natalie or a graduate student. I have 4 copies of the 6-month license for Stella 9 that are up for grabs, that I've offered to the other folks, the undergraduates who haven't, who aren't going to get licenses otherwise. So the first 4 people who say, "Hey, I want a license," is going to get one. Otherwise, they'll just go to waste. I got 20 because I got a pretty good discount for quantity if I did 20. So that's where we are on Stella. That should happen anytime. And if you're using Stella 9, the demo, it's going to time out on you pretty soon now. So you'll need to convert over to the licensed version. Fast playback, still a continuing issue, but thanks to Ray Camps, I think we're making some good progress, and there's light at the end of the tunnel, but I haven't seen it completely yet. Some people may have some success with Windows Media Player on Windows 7, but I have not. I tried again with a different machine, and every machine I've tried, if you try to go to fast playback, the audio and image parts get out of sync pretty quickly, and I think the image leads the audio is the way it works. Ray's had the same experience. But Elizabeth out in Oregon says that she's been able to successfully use Windows Media Player at speeded up rates. VLC, I can't get to work at all on Windows 7 to play back even AVI files. I think people here in the room had the same experience. It worked fine with XP, but it doesn't work in Windows 7. And of course, you can do speeded up playback of IrfanView in XP just fine, but not in Windows 7. So that's the problem. You're lucky if you still got Windows XP, I think. But maybe we're going to be able to do a workaround using the discoveries that Ray has made that involve converting the AVIs to MOV files, MOV, which play then on QuickTime. And you can actually do a speeded up playback with QuickTime that seems to work on Windows 7. So that's where we are on that. I think that's it for housekeeping. Let me get on down to where we stopped last time. I think I'm going to get out of the show so I can speed ahead here. And let's see. Looking for a landmark I recognize. There's one. So we're in respiration part 2. And I was talking about Fick's law as it applies to gases, and I explained that, you know, as it applies to gases, you need to work in partial pressure instead of, at least for oxygen, you need to work in partial pressure instead of concentration terms. I told you what the representative partial pressures of both oxygen and carbon dioxide were at different points in the circulatory system of a representative fish. Pointed out there's lots of variation depending on what kind of fish and how much activity that fish has. So those were just ranges of values, and I'm going to use some of the midpoints there, or representative values, a subset of them, to sort of work you through. Here, by the way, are the solubility coefficients that are relevant to my little example I'm going to work through. And what I've got are Bunsen coefficients for oxygen, carbon dioxide, and nitrogen in freshwater and seawater at 2 different temperatures, 5 degrees and 25 degrees. And you can go on the web and find them for every other combination you can imagine. And the reason I want to work with these is I want to talk to you about an example. And the point I want to make is that, well, before I get to that point, let me just do this little example here about how to calculate concentration of gas given a partial pressure. So the question I raise is, how much oxygen will be expected to dissolve in seawater at steady state at 25 degrees? And the way you get the answer to that kind of question is remembering that Henry's law says that it's the Bunsen coefficient multiplied by the partial pressure of the gas. And so I'm backing off a step and I'm talking about the proportion of gases that make up normal air that is oxygen. And so we get the partial pressure of oxygen in a steady state situation by taking 21% of 760, that's total, which is about 160. And then multiplying that, I guess I lost my error when I went back to this slide view. Okay, by multiplying that by the appropriate value for oxygen, looking in the table here, seawater, 25 degrees, is 0.03. And the dimensions of Bunsen's coefficient that I've got tabled here are in milliliters of gas per liter of solution per millimeter mercury partial pressure of that gas. And so what you end up with are a volumetric concentration, milliliters of gas per liter under standard temperature and pressure conditions. If you want to get to a concentration in mass units per liter, then you multiply it times the atomic weight of the gas, which is 32 in the case of oxygen, and the number of liters occupied by one, well, it's actually the number of grams of gas, I guess, in the mole, or grams in a mole, divided by the number of liters occupied by that ideal gas. And that's 22.4 for everything. And so you end up with, I think what I had here was 32 millimoles per milligram, or per milliliter, basically. So I end up with milligrams per liter in my dimensions. I mean, a mole per liter is the same as a millimole per milliliter, right? And so we need to get the milliliters out of here. We want to go to milligrams per milliliters. Is anybody checking my math here, checking my dimensional analysis of this thing? My question has to do with a subtle one, which is, what are the dimensions of this ratio? And I know that 32 grams, I know that 32 grams of oxygen will occupy a volume of 22.4 liters. So it's grams per liter, but it's also milligrams per milliliter, I guess. One mole is 32 grams. 1 millimole is 32 milliliters. And so if this is 22.4 milliliters, then that milliliters goes out, and we end up with milligrams per liter here instead of milliliters per liter. That was the whole point. Sorry about that. I know you're all intensely concerned about that. Well, you need to be if you're actually going to do any kind of calculations. And I've explained before that I'm willing to accept that a milligram per liter is the same as a part per million. So, you know, the number of milliliters of oxygen per liter, that is always a little less than the number of milligrams because of that ratio of 32 to 22.4. So you end up with 6.84 milligrams is equivalent to 4.79 milliliters. So you could do a couple of these others, you know, just to test yourself to see if you got it under control for oxygen or nitrogen or what. You know, if you're working with nitrogen over here, you'd have to be converting to 0.79 or 0.8 or something like that, right? Because nitrogen makes up 80%. And then be using the nitrogen coefficients. So here's where I want to go with all this. I want to use Fick's law and work through it to compute oxygen uptake of an ecofish or any other representative fish, and the rate of carbon dioxide excretion. And the argument I want to make is that we would expect, if everything is working the way it ought to, and the fish is metabolizing a normal mix of substrates, that we would have about 1 mole of carbon dioxide produced for each mole of oxygen used, or millimoles. And so I want to test to see if I can show that makes sense. I want to actually do the calculations and see if I get that result using the typical values of everything. And so I'm going to assume fish in seawater at 25 degrees centigrade. For oxygen, the Crow coefficient, and you have to take my word for this, this is a tabled value, is 9.9 times 10 to the minus 10th, and look at the dimensions on that. Milligrams of oxygen per centimeter per millimeter mercury pressure per second. Those are the dimensions of the Crow coefficient. The anatomical lamellar area we're going to assume of this representative fish is in the middle of the range that I gave you, 2 centimeters squared per gram of body weight. And we're going to assume that 25% of the anatomical area is actually functional. So we're at 0.5 square centimeters per gram for A, the area. The diffusion distance I'm going to suggest is 2 microns of epithelium and another 8 microns of boundary layers on the 2 sides, blood and water, that all have to be diffused across. So a total of 10 microns. A micron is a millionth of a meter. And it works out to 10 to the minus 3rd centimeters. Okay, so you, I hope, are buying these numbers as being at least reasonable, if not the absolute truth. Computing oxygen uptake rates and CO2 excretion rates by Fick's law to continue. I've got some values here that I have to use for oxygen and CO2 partial pressures in blood and water. And what I'm going to argue is that the blood comes into the gill exchanger with 10 millimeters partial pressure of oxygen and 7 millimeters partial pressure of CO2. And the water comes into the exchanger at 140 for oxygen. This is air-saturated water or thereabouts, nearly air-saturated. It'd be 160 if it were completely. And near zero on CO2. So it's good water, with the low CO2 content. And then the blood exits the exchanger with an oxygen partial pressure of 65 and a CO2 partial pressure of 2. And the water is 100. We've given up some of the oxygen that was in the water. It's down to 100, and the water has picked up some of the CO2. It's up to 2. And so then I've calculated average values halfway through the exchanger for oxygen and water and CO2 and blood and water, and I've arrived at a blood-water difference of 82.5 millimeters mercury partial pressure for oxygen and a 3.5 for the CO2. And the minus, I'm calculating this as a blood-water difference, so I got a negative difference for the water here and a positive difference for a negative difference for the oxygen and a positive difference for the CO2. So now we can do the computations because we got all the numbers that we need to solve the equations for the two different gases. And Fick's law for oxygen is this one, and for carbon dioxide it's this one, using the Crow coefficient for oxygen and CO2, using the same values of area because the oxygen is going through the same functional area that the CO2 is coming out through, and the diffusion distances are the same. But the partial pressure differentials are different, and those are the values that I was calculating over here. I had to find something, and what I did was calculate an average value halfway through the exchanger for each gas. And so those go in here as dPO2 and dPCO2. And when I get all done with the calculation using those values, I end up with DO2 dt is plus 0.147 milligrams of oxygen per gram of body weight per hour. If you think back to the results of the lab that you just did for ecofish, that's in the range. It's 0.2 of a milligram or less. It's 0.15 or so. And CO2 is not that far, off. It's a minus. The plus sign indicating that oxygen is taken up at the gill into the blood, and the minus sign for CO2 indicating the flux there is in the opposite direction, from blood to water. And so I ask, are the numeric values right or wrong, and are they in the right range at least? And you have to be concerned initially, probably, unless you're already jumping ahead and doing respiratory physiology like Allison does, that there's more of CO2 coming out than O2 going in. Does that mean that this fish has got a respiratory quotient that's not 1, which is what we were talking about, a 1-to-1? Maybe it's burning more fat or something, or doing something different. And of course, if you're thinking ahead, you already know that, well, that's really not it. It's the fact that the molecular weights of the two gases are different. And so when you convert things to a molar basis, which is the argument that you have to make, it's not a milligram of oxygen used per milligram of CO2. excreted. It's a mole of oxygen used per mole of CO2, or millimoles. And when you do that conversion, VO2 is about right for a retaining active fish, and VO2 and VCO2 are almost perfect complements on a molar basis, because 0.147 milligrams of oxygen is 0.0046 millimoles, and 0.217 milligrams of CO2 is 0.0049. So did I make sure that these numbers worked out, by making sure I made the right choices back there, Did I have to go back and do an adjustment or two? Yeah, probably. It's been a while. I don't remember exactly what I did, but I suspect, Tyler, that I went back and made an adjustment. But if I'm convinced Allison, who's done a thesis in this area, that maybe you all would be convinced. Does this sound reasonable to you? Yeah. Good. So all in the world I did was use Fick's law to arrive at a result that is consistent with expectation. Just showing you that everything's internally consistent, or could be made consistent with a little bit of a squint and a nod, Okay, so now let's move on and talk about something inside that whole business, and that has to do with the relationship between binding of oxygen and release of oxygen by the hemoglobin, and the physics and chemistry that are going on in the system. And it brings us to a consideration of the Hill equation, which is a special case. I'm thinking A.V. Hill maybe was the guy of the power hyperbolic that you would find if you looked in that Excel file that I made for you. And I hope you'll do that. It's kind of a test of your curiosity, because I'm not going to ever do that. I'm not going to open that file. I want you to open it, and I want you to put in different values of the P50 and fiddle with it and see what the curves look like when you put in different trial values. I'm going to show you a representative value that's pretty much without real quantification. But the argument is that the amount of oxygen that will load to the hemoglobin is a fraction of the capacity of that hemoglobin, which depends on lots of stuff, including how much hemoglobin there is, and its specific molecular nature. And different fish have different kinds. Even within the same species, there are different types of hemoglobin, different subtypes. What we're saying is that the amount loaded is the fraction of the capacity, and that fraction is the ratio of the partial pressure of oxygen in the plasma in the environment of the hemoglobin divided by a parameter, the P50, raised to a power n, and then divided by 1 plus that same ratio to a power. And this, where oxygen load is milligrams of oxygen associated with bound to hemoglobin per unit volume of blood. O2 capacity is the saturation value of O2 load. P is the PO2 in the blood plasma, and P50 is the value of P causing half saturation. N is a constant, or is maybe a constant. Most people treat it as a constant, which has a value in the range of 1 to 3 for fish, and the average value tends to be up 2.7 for fish hemoglobins. It's 1 for the muscle form of the pigment, which is called myoglobin, and hemoglobin has 4 of these heme units. I'm not going to talk about the molecular structure so much, but just tell you that hemoglobin has 4 heme units, and it's the folding of the hemoglobin molecule in 3-dimensional space that affects the interaction of the different heme units to bind an oxygen molecule, and each one that's bound affects the binding of the next one. Heme only has 1, or myoglobin only has 1 heme, so it's not going to have this power. It's just going to be a straight hyperbolic instead of a power hyperbolic with a power of 1. So that's the shapes of the curves. The power hyperbolic has a sigmoid shape, and I've exaggerated it here because the P50 as a function, well, I guess it all depends on what scale, but typically what you see is a very small lag. The P50 sitting way over here to the left somewhere near the origin, and so it's a little bit and then straight up nearly. So this would be n equals 3. And then here's the myoglobin relation for the same P50, where you don't have an inflection at all. It's just a hyperbolic, straight hyperbolic. But they cross at this point where we have half the capacity occupied or used, and we're at the P50. So I do encourage you, though, to open up that Excel file and find the page or the sheet that has to do with the power hyperbolic and try out different values just to see what the curves look like for yourself. I've already told you that N is a measure of the interaction among the various heme units within the hemoglobin molecule. And it's 1 because myoglobin only has 1 heme. Oxygen capacity is the maximum value of O2 load. It's the amount of oxygen that fully saturates a unit volume of blood. And for fish, the typical value is somewhere between 10 and 15 milligrams of oxygen per 100 milliliters. Sometimes that's called oxygen percent. What is it called? It's called volume percent, or it's called mass percent, I guess, in this case, because it's the mass per 100 units. So it's 10 to 15% if you're calculating per 100 milliliters and you're talking milligrams. If it's 10 to 15 milliliters of oxygen per 100 mils, then that's volume percent. I'm not sure there's any point in getting confused by talking percent. It'd be better just to stick with the actual dimensions. Oxygen affinity, that's capacity, is the amount of oxygen you can bind to a unit amount of hemoglobin. How do you do it? Well, you take some blood, fish blood or whatever, and you expose it to a very high partial pressure of oxygen in an artificial situation for some period of time, trying to keep it from clotting with heparin or something while you do that. And then you finish, and then you try to pull a vacuum and you pull off and see how much oxygen you can get off that blood as a function of how much blood there was, or what volume of blood you had to start with. So if you had 100 milliliters of blood in a petri dish, I guess you would figure out how much oxygen you get off that when you pull a vacuum, and if it's 10 to 15 milligrams, that would be what you'd expect. O2 affinity, on the other hand, is sort of how much attraction in a kind of a touchy-feely sense there is of the hemoglobin for the oxygen, or of the oxygen for the hemoglobin. It's measured as the magnitude of the P50. And the smaller the P50 is, the nearer the P50 is to 0. That is, the lower the partial pressure of oxygen in the plasma is that's necessary to cause half saturation of the blood or the hemoglobin with oxygen, then the greater affinity that blood is said to have for oxygen. So just keep in mind the relationship is an inverse one. Infinity increases as P50 goes down, or P50 goes down, infinity increases affinity. Not infinity, affinity. So some effects of environmental factors on this set of relationships. One of these is the Bohr Effect. And I would define the Bohr Effect as a decrease in the oxygen affinity, not the capacity, but the affinity of the blood caused by a decrease in either pH or sort of the complementary change, an increase in the partial pressure of CO2. And with fish bloods, that tends to be the same thing because, as I think I've already said, fish blood's not very well buffered, so for changes in PCO2, you're going to get some pH swings, not so much in mammalian blood, maybe. The importance of the Bohr effect is that where you've got high PCO2, as you would have in the capillary networks in the tissues, where you want to get rid of CO2, or you're going to get rid of CO2, hopefully, then that facilitates the unloading of oxygen from that hemoglobin, because when CO2 increases, the partial pressure of CO2 increases in the plasma, that reduces the affinity of the hemoglobin for oxygen, so you get a shift, a Bohr shift, and that tends to release the oxygen, which is what you would want to happen, right? Because the whole goal is to get the oxygen into the tissues. And I guess I got a figure here to sort of illustrate the general point that I just made. It's a very generic, idealistic figure, but what I'm trying to show here is the position of the dissociation-association curve as a function of PCO2 or pH conditions that would cause a Bohr shift when there is a Bohr shift. And so, this left position here is the situation for low PCO2, near zero, pH near neutrality. And then in the tissues, where pH tends to drop because of the elimination of CO2 and maybe some other things, there's a shift to the right in the shape of the curve, so that the P50 is moved from a position here in the gill to a position to the right in the core of the fish, the tissues that are actively metabolizing. So, what this achieves for the fish, or for any animal, is that in the gill, where PO2s are high, we can almost completely load the hemoglobin, say, better than 95% of capacity with oxygen. So what you have to think is, hey, here's the PO2 in the gill, and the relevant curve of these two is this curve, and so the point at issue is this point here at the tip of my pointer. And that's where having a speeded up playback that actually works is really important, because I say right here at the tip of my pointer, and if I had already moved my pointer over here when I said that, that wouldn't be good, right? That'd be very confusing. So in the gill, PO2 is high, and we achieve an oxygen load on the hemoglobin that's almost the capacity. And then as that blood passes from the arterial side into the tissue capillaries, and PCO2 increases due to the elimination of CO2 from the actively metabolizing tissues, and maybe the pH starts to fall, then the curve shifts to this position. And that doesn't matter. That's irrelevant at that point. But the point that matters is this one here now, because there is the intersection between PO2 value in the tissue and the oxygen dissociation curve. So when you look at this, you can see that having a Bohr shift might achieve for you a delivery per pass or per unit volume of a lot more oxygen per unit blood than you would get if you didn't have a Bohr shift. Can everybody see that? Could you explain back to me on the exam why a Bohr shift could facilitate maximizing the transport of oxygen? In other words, what you need to be doing is drawing little brackets here like this, where you show me that, hey, without a Bohr shift, how much oxygen could you get? Well, you could get an amount from there to there. Or maybe if you had the other curve, you could get an amount from there, and pardon my rough drawing here, to here. So, you know, what I'm trying to show you is that difference if you use the red curve, this difference if you use the blue curve. But if you can use both curves, then you can get this difference. Right? Which is greater. So having the shift allows a greater difference between loading and unloading amounts. My curves are ragged. You ought to draw your own on the handout. Be sure that you can kind of do this, because I might want you to. Can I say it any more plainly? Okay. So, the Bohr shift or the Bohr effect means that higher PCO2s in the tissue permits more oxygen to be unloaded from the blood than would be possible otherwise, at least ideally. The associated effect that everybody loves to talk about is the root effect. And, you know, I guess the Bohr effect is named for Niels Bohr, N-I-L-S, Bohr. I'm not sure about root, who that was, or if it was someone. The root effect as defined is defined as a decrease, not a change in affinity, but a change in capacity. And it's a decrease in the capacity that is caused by a decrease in pH. In other words, the same cause, but a different result. Decrease in pH or increase in PCO2 causes a decrease in the capacity of the hemoglobin to bind oxygen. And the biological importance of that is really not that much for ordinary respiration, but it's tremendously important, as we'll learn in swim bladder dynamics. Why is it not that important in ordinary respiration? Because, you know, what we're talking about are things that go on at very high partial pressures of oxygen, higher probably than you'd ever encounter in the water. Except in the case of liquid oxygen applications in aquaculture, you know, and maybe there the Bohr effect, both the Bohr and the root effects can become important in terms of maximizing transport of oxygen. Because what happens is that when pH increases, pH decreases or PCO2 increases, the shift is not in the P50 so much necessarily, although here I think I'm probably showing some of each. It's a decrease in the capacity. In other words, no matter how much oxygen you got in the plasma, you still can't get the hemoglobin to bind more oxygen than that amount. So in this case, the capacity is reduced by 40%, looks like. So imagine you got a tank full of fish under really intensive aquaculture conditions, and they are producing a lot of CO2, so much that it stays in solution and rises to a very high partial pressure. And the result of that might be that, you know, the fish can't unload, they can't load oxygen at their gill because the PCO2 is real high in the water. Unless you give them a whole lot of oxygen, you know, and if you give them enough, maybe you can do something about that. But this root effect would say that even in very high oxygen partial pressure situations, you couldn't get more than this amount. So really it's a Bohr effect, I guess, that we'd be talking about in the case of, let me go back a notch here. I think I misstated and in my case, I've not drawn my figure very well. You know, it might be that the Bohr shift would be so great that the red curve would be way over here, and the normal PO2 in the water would be back here, so you wouldn't be able to load oxygen. But if you had enough oxygen, maybe you can still achieve something close to saturation. Maybe I shouldn't have brought up the aquaculture. If you followed the logic there, you probably figured it out anyhow. So while I'm here, I'll point out that one of the things that's important is the timing, the temporal dynamics of these shifts. And in the case of the root shift, at least in eel blood, I guess, probably, thinking about this, it's been demonstrated that the root on shift is very slow compared to the root off, and that turns out to be critically important, as we'll see a little later in swim bladder dynamics. 90 milliseconds to do a root off, and 9 seconds to do a root on. So 9,000 milliseconds versus 90. And I like to explain that to myself, at least, by saying it's kind of like the child's game of ball and jacks. Did you ever see that when you were a little kid? You know, and you can pick up those, that 10 jacks, and you can drop them very quickly. But to gather them all up, takes a little longer. So I think it takes longer for the hemoglobin to gather up the oxygen than it takes to release it.
So in this case, root on means loading with oxygen?
It means, gaining oxygen that is in solution when your shift is to this position. So if you have PCO2 low and pH at 7, then that increases your capacity, and you could take more oxygen up if you got enough time, but you have to have time. And so we'll see a little later when we're in the swim bladder reet and the blood is coming back to general circulation and exposed to very high partial pressures of oxygen. It still doesn't load the hemoglobin back completely. It'll become clear when I talk about that. Julie? It logically would, but I think the timing of the circulation is slow enough so that it's not so dramatic there. It takes a while for the blood to move through those tissues, and so probably there's enough time. But I suspect that it does affect it, and I think that's why the hemoglobin is still taking oxygen up when the blood has already left the gill, and reducing the plasma concentration, so it doesn't, you're not. Otherwise, it's hard to understand why the partial pressure of oxygen in the plasma of the blood leaving the gill in the dorsal aorta wouldn't be at 140 or 130 or 20 even. Why is it all the way down at 50? I think it's because the hemoglobin is still sort of harvesting that. But I may be wrong about that. I don't know a lot about the molecular level stuff here. Question that Julie asked for people on the record, and maybe I didn't re-ask your question, was does this time differential, this timing of on and off occur with Bohr shifts as well as with root shifts? And I don't see any reason why they wouldn't, except that I think the transit of the blood that's relevant in the Bohr shift is slow enough that it's probably less important there than it is in the swim bladder reet, where you're talking about less than a second. And then Ray's question was, when you talk about on, do you mean loading of the oxygen onto the hemoglobin? And yes, that's what I mean. An off shift is releasing it, and an on shift loads it. So there are effects of temperature on oxygen association, dissociation, as there are nearly on everything else that goes on. And the effect of the temperature change is analogous to the Bohr shift, but it's not a Bohr shift, it's a temperature shift. And it has to do with a decrease in the oxygen affinity of the blood caused by an increase in the temperature, sort of analogous to a decrease in the oxygen affinity caused by an increase in PCO2. PCO2 thing is a Bohr shift, but temperature thing is just a temperature shift. The magnitude of the temperature effect typically is about 1 millimeter mercury change in P50 per degree. So for every degree of increase in temperature, you get about a 1 millimeter mercury shift in the P50. Trying to remember where I need to say various things here. Maybe that'll come up naturally enough in this sort of ecological generalizations, as I call them, that have to do with this oxygen association-dissociation business. And I think I've got about 4 of these generalizations to present to you. First is that the affinity of a fish blood for oxygen in general terms tends to be inversely proportional to the richness of the habitat in oxygen. So the more likely the water in the habitat of the fish is to be air saturated with oxygen, the more you would expect the fish to have relatively low affinity. It's inversely proportional. And the example fish I've got are rainbow trout to carp. Carp representing a fish that lives in a habitat that may be oxygen deficient a lot of the time. High affinity, 5 millimeters mercury. It only takes 5 millimeters mercury partial pressure in the plasma of carp blood to achieve 50% saturation of the hemoglobin at steady state. A rainbow trout, on the other hand, and other active fish from oxygen-rich habitats tend to have lots lower affinity, so it takes 18 there. Toadfish, I show there just because toadfish is not a real active fish, but it lives in an air-rich, fairly oxygen-rich habitat, so it has fairly low affinity. So the affinity is more related to habitat DO than it is to the general level of activity of the fish. I wouldn't want you to get the idea that the rainbow trout has low affinity because it's active. It's got low affinity because it lives in a habitat that has relatively high oxygen. Now, the capacity does tend to relate to activity. And there the rule is that the more active the fish, the higher its capacity. In other words, the more oxygen it can carry per unit volume of blood in its blood bound to hemoglobin. And here I'm using volume percents. So what I'm talking about is milliliters of oxygen per 100 mils of blood, I think. And that's because that's the way the numbers are tabled in the literature. And here I use the toadfish again just to show you that even though the toadfish has high affinity, low affinity, I guess, a high P50, because it lives in a fairly oxygen-rich habitat, doesn't mean it has high capacity. It's got only a 6.2, so that relates more to the level of activity of the kind of fish we're talking about. Mackerels, which are highly active fishes, have 15.7. And I'm not sure about typical mammals, but I'm thinking that numbers in the 20 to 30 range are right for mammals. Anybody know? I just sort of remember that. I don't have it in my notes here, I don't guess. So is anybody confused? Did I leave you confused? That's the way to put it. Not did I make you confused, but did I leave you confused about the toadfish situation? Relatively low affinity, high P50, which is characteristic of fish that live in oxygen-rich or at least not deficient oxygen habitats. But a relatively low capacity because the toadfish is sort of an inactive fish compared to these others. And then the third of these generalizations is that the strength of the Bohr effect, or how marked the Bohr effect is, tends to be generally proportional to habitat dissolved oxygen richness, and maybe secondarily to the level of activity of the fish, but probably mostly habitat DO. So here are some Bohr effects measured in terms of the change in the P50 for a 10 millimeter mercury change in the partial pressure of CO2. And for the Fish that live in oxygen-deficient habitats like the catfish, relatively, I guess, and the carp and the bowfin, we're talking less than 10. But for mackerels and tunas, more than 45. So, the explanation that people usually offer for this kind of relationship is that fish that live in oxygen-deficient habitats often may deal with habitats that have a lot of CO2. And so if you were a carp or a bowfin and you lived in water like that, then you might not want to risk having a good, strong Bohr effect, because if you did, the Bohr shift might occur in your gills instead of in your tissues. And then that would prevent your blood from being able to load as much oxygen as it would otherwise be able to do. So I think the way it's usually written in the textbooks is that fish like bowfin and carp can't afford the luxury of having a good, strong Bohr effect, whereas tunas and mackerels, which live in air-saturated habitats, you know, they're very active, so they need all the oxygen to be transported they can manage, and so they have good, strong Bohr effects. And I guess I say it there. Oh, there's one other thing that I didn't mention already, and that's the electric eel. I claim that's the exception that proves the rule, and that's not my claim, that's somebody else's, obviously. That it has one of the largest Bohr effects known, and yet it lives in oxygen-deficient water. So how can that be? And the answer is that it doesn't breathe the water, it's breathing air, which is rarely with a lot of CO2. So it's not having to deal with the risks of breathing water that has high CO2. And then finally, temperature effect tends to be most marked in stenotherms, fish that live in water that has less variable thermal conditions than other fish. Fish that live in highly variable thermal regimes that we call eurytherms can't afford the luxury of a large temperature effect, because regularly they might encounter high temperatures at their gills, and that would prevent them from being able to load as much oxygen as they need or could without the temperature effect. So if you live in a very stable thermal environment like salmonids typically do, you don't need to worry about high temperature maybe at the gills. Maybe you do nowadays with the deforestation of the Columbia Basin, but evolutionarily they didn't. So they can use the temperature effect to help unload the oxygen at their tissues, because there the temperature is a little bit higher due to metabolism. Tunas, you'd think, would be the perfect case for a fish to use a temperature effect to enhance its own capacity to supply very active tissues, because tunas are warm-bodied. And so wouldn't it be nice if, you know, the blood, when it reached the tissues and warmed up, were able to release the oxygen, because the increase in temperature lowered the capacity of the hemoglobin for oxygen. And so it turns out, though, that it doesn't work that way. And it doesn't work that way because, and this I think was either, and it's been so long now I can't remember, two famous tuna physiologists and ecologists. One, Peter Hochachka at the University of British Columbia, and another, Frank Carey, who was at Woods Hole, worked on tunas. And one or the other of those two folks, I think it was probably Hochachka, demonstrated that the temperature effect was not strong in tunas, and reasoned that the reason it's not strong is because the temperature increase that occurs in tuna blood doesn't happen so much in the tissues, it happens in the countercurrent exchanger. And the risk is that in that situation, you might get oxygen coming out off the hemoglobin and actually reaching such high concentrations of such high partial pressures that it forms bubbles or emboli, which then plug the capillaries, cause a stroke basically. So at least that was the argument, and I don't know if anybody has made any correction to that argument in recent years, but that's the way it was left in my mind, is that the risk of oxygen embolism in countercurrent heat exchangers of tunas is a force that has prevented them from adapting or evolving this capacity for high temperature effects. Gas bubble disease is a special issue that has to do with oxygen solubility and binding of oxygen to hemoglobin. And the reference I would offer here is a dated one now, but it was a full issue of Transactions of the American Fisheries Society devoted to gas bubble disease. The argument is that supersaturated gases come out of solution and form bubbles. And then those bubbles lodge in capillaries like in the gills and the brain and block blood flow. You can also see the effects, they're more conspicuous but probably a lot less critical in the formation of bubbles just under the skin surface, in the thin membranes, and in the capillary bed behind the eye, which causes the eye to bulge out. There are other conditions, parasitism, that causes the same pop-eyed condition. But all of these things can happen when fish live in situations where oxygen or gases are supersaturated. I won't say oxygen. I'm going to come back and tell you that I don't know any natural case where oxygen supersaturation alone has been responsible for causing gas bubble disease. In all the cases I know, it's either nitrogen or nitrogen and oxygen together as supersaturated air. And this is, as I say here, one of the few fish diseases, maybe the only one, that has a very clear, clean biophysical basis. You can sort of understand it from beginning to end just on the basis of biophysics. And here it is, Henry's Law. We talked about that. Concentration linearly proportional to pressure, but not linearly related to temperature. Dalton's law says that total gas pressures is the sum of the partial pressures of the gases. And here are the partial pressures of the ordinary gases in air under normal conditions. And I've already laid some of these out. There's that 160 for oxygen. And it's for nitrogen and argon together at 600. Most people use 600 just because that's a nice round number for nitrogen's partial pressure. And 5 at 0 degrees at least for water, which turns out to be water vapor exerts partial pressure as a gas, and so you have to take that into account as part of a moist environment. It's not in dry air, of course, but it's there in ordinary air. And the air that's in water is certainly wet. So gases are held in solution partly by water pressure, and that means that we need to distinguish between what's called relative saturation and absolute saturation. And relative saturation is defined as the pressure of the gas in solution divided by the pressure of the gas in the gas phase multiplied by 100. So relative saturation, and this has always confused me because the labels seem like they're counterintuitive. Relative saturation, let's say you've got a volume of water that's uniformly mixed, well mixed, and at equilibrium with the gases in the atmosphere. Then the relative saturation of that gas will be the same from top to bottom in the water. So the relative saturation is a constant then for the situation. If the pressure of the gas is, if we're talking about oxygen, and it has 160 millimeters partial pressure in solution, it has 160 millimeters in the gas that's in equilibrium, the air above it, then that's 1 times 100 is 100%. So oxygen would have 100% relative saturation from top to bottom. Or if, the amount in the solution were reduced by biological activity or for whatever reason to 0.8 of 160, whatever that would be, then we would have 0.8 times 100 or 80% solution, or 80% relative saturation from top to bottom. But absolute saturation depends not only on the gases in solution and in the atmosphere with which that solution is at equilibrium or in the same system with, it also depends on the partial pressure of water, or the total pressure of water, not the partial pressure. Let me rephrase that. I don't want to confuse anybody on that point. P is hydrostatic pressure, or pressure of the weight of the water bearing down on a point. H2O then would be 0 at the surface and would increase with depth. And you already know how much. It would increase by 1 atmosphere for every 10 meters approximately. And so given the same partial pressure of a gas in solution exposed to the same air above the solution, the absolute saturation is going to go down with depth. In the case that I first described, where you got 160 oxygen and 160 in the gas above the water, that's 1. It's 1 over the total pressure exerted by the water plus the gas, so it in effect goes down about 10% per meter, at least initially. So measuring in the same dimensions as might want to think that through before I lay out numbers. Let me just stop here. We're close enough to the end. No, let's don't. Let's work this out together. Partial pressure of oxygen in atmospheres is 0.21 in solution and in the gas above the water. So we got 0.21 over 0.21 plus the pressure of the water, where water is going to be 0.1 atmospheres for every meter we go down. And so at the surface, we would have 100% absolute saturation of oxygen in that water. And what would the saturation be at 1 meter? It'd be 0.21 plus over 0.21 plus 0.1, so about 70%. Is that right? And then as we go down another meter, we're gaining another 1/10 of an atmosphere of water, but we're not changing the PS or the PG values, so it's 0.2 plus 0.2. So we go down to 2 meters, we're already at 50% absolute saturation of oxygen. And what happens, is it linear? Can we go all the way to 10 meters and make this all work? Well, I think we need to actually graph it out to see the shape of the relationship between absolute saturation and depth. And maybe that'd be a good challenge for you to see if that's a linear relationship. I don't think it's going to be, because at a depth of 10 meters, we're going to have 1 plus 0.21, or 1.21 divided into 0.21. And I don't think that's going to be half of what it would be at 5 meters. In other words, it's not going to be linear. Where does this get important? It gets important in consideration of gas bubble disease. Gas bubble formation depends on absolute saturation of gases rather than their relative saturations. It's absolute and not the relative saturation is important, because the propensity or the likelihood of a bubble to form is defined as the pressure of the gas in solution minus the pressure of the gas in the atmosphere with which that solution is not in equilibrium, but in contact, I guess would be the right word, less the pressure exerted by hydrostatic pressure of the water. And the propensity of bubble formation will be 0, in which case, somebody do the math for me here. Let me see what I say in the next. Didn't help myself there. I think it will be time to stop and let me reassess here before I tell you wrong stuff. I think what I'm going to argue is the propensity for bubble formation only is positive, obviously, when the sum of those three terms is positive. So if partial pressure is high enough to offset the pressure of the water, then you have a bubble, the possibility of bubble formation, because it'll be non-zero. Am I right or am I wrong? I'll work that out and get back with you then next time, because I'm forgetting the details at this point.